Hello, good afternoon, everyone. I hope you're ready for today's session. Yes, my name is Kelvin Muli. I'm a GIS and expert from Kenya. So today I'm going to take you through a topic by the name remote sensing, future trend and opportunities. And by that, first, I would like to welcome you all for today's session. And I'm so privileged to be with you today. And I believe that we are going to learn more today. So basically for today's lesson, we're going to look at some of the issues we're going to learn about remote sensing, and we're going to enjoy it. So first of all, allow me to just make a few changes here before we start. Okay, just a few minutes. Yes, it's okay now. So as I was saying, let me introduce myself again. My name is Kelvin Muli. I'm a GIS and remote sensing expert from Kenya, and I'm going to take you through remote sensing, future and trend opportunities. Last time we covered GIS, and today we're going to look at remote sensing. And I've prepared something beautiful for you guys today, and I hope you're going to learn. So first of all, I'd like to give a definition of what remote sensing is. Remote sensing is actually obtaining information from an object without having direct contact with it. You see, you can obtain information about someone, something, anything by being there physically, by touching it, knowing its texture, complexion. But for remote sensing, it's actually obtaining that information of an object or anything without actually being in direct contact with it. That means you're able to get information about that object through other means, which I'm going to show you. And there are two types of remote sensing. We have what we call passive remote sensing, and we have what we call active remote sensing. For passive remote sensing, as you can see on the screen, is the kind of remote sensing where the source of energy is either the sun, the earth, or the atmosphere. And for this case, as you can see in this diagram that I've shown here, where the sun is the source of energy, it's giving out the radiation to the earth surface. And then from there, the sensor is able to obtain that energy. And then we have also what we call active remote sensing. And in active remote sensing, source of energy is part of the remote sensing system itself. That means the remote sensing is able to produce its own energy, and that's the beauty of remote sensing. That means, and I'm going to give you the difference and how you can be able to see the difference between the two. In passive remote sensing, it means sun, you cannot obtain information or data if the sun is not there. But in active, that means you can be able to obtain this data even at night because the sun is not there at night. That means during the day we can use either passive or active, but during the night we use active remote sensing where the source of energy is part of the remote sensing system, and it produces its own energy. And then from there, we're going to look at what we call the components of remote sensing, which is also very important because you need to understand what comprises of this remote sensing system. And remote sensing comprises of two components, where one is the platform and the other one is the sensor. And what is a platform? A platform, this is the vehicle that carries the sensor. For example, a satellite, for example, aircraft, for example, hot air balloon. For instance, I've demonstrated here. This is an hot air balloon. And then we have the sensors. This is a device that receives electromagnetic radiation and converts it into signal that can be recorded and displayed as either numerical data or an image. And a sensor, for example, I'll give you another key important. That means a platform can be able to carry more than one sensor. In today's century, I'll give you the real life examples where we see a platform. We have satellites. I'm going to discuss about satellites as we continue. Aircraft, like for drones, I'll give an example of drone. A drone is one of the platform, and also aircraft. Aircraft, institutions that have that capacity, where you mount some cameras, some cameras on the aircraft, and then the aircraft is in the sky, and it's able to take aerial images on the ground. Then sensors, these are examples of sensors. These are devices, that's able to tap that information, that electromagnetic radiation, and then it converts it into a signal. And examples of a sensors can be a GPS. GPS is one of the examples of a sensor, because a GPS is able to convert that electromagnetic radiation and convert it into a signal. And using a GPS, for instance, you can be able to see even the number of satellites in the sky at that particular time. So the two components of remote sensing, that is the platform and also the sensors. And then now, as we go further, we're going to look at some other things. And the next thing, we're going to look at the types of satellites. As a GIS and remote sensing expert, you need to understand what are the types and uses of these satellites, because every task you undertake as a GIS expert and a remote sensing expert, you need to understand the kind of satellite you use. It's what does it do, how does it work. So I'm going to give you the types and uses of satellites that we have, and we're going to divide them into three categories. And the first category of satellites, we have the low orbit satellite, the low orbit Earth. These are normally used as spy satellite mostly by the military purposes. The low Earth satellites, they're not very high in the sky. They're actually very close to the sky. And examples of these low orbit satellites, we have Landsat images, or Landsat satellite. They're very close to the sky, meant to the Earth, but you can be able to, even using microscope, telescope, you can be able to view them. You can see them. And then we have the second category of satellites. We have what we call the sun synchronous orbits or satellite. These ones, most of the time, they are Earth resources satellites. What do I mean by Earth resource satellites? Earth resource satellite. These are satellites that provide data based on the data on other resources. Other resources, we have water. Other resources, we have vegetation. Other resources, we have mountains. We have climate change. We have sunlight. We have soil. All these are which all these have other resources. So these satellites are mid-air. You see, there's three categories of the low, there's a medium, and the higher level satellites. So these are actually at the middle after the low Earth satellite. And then the third category of satellites, we have the geostationary satellites. These are at very, very high altitudes. They're very high. You cannot actually see them using this normal telescope. You need a very, very high modern telescope to view them. And these are used for meteorological applications, which give us the daily weather updates. And all these are very important to a remote sensing person or anybody who is interested to become a remote sensing expert. We need to understand the three categories. So we have the low Earth orbit or satellites, we have the sun synchronous satellites, and also we have the geostationary satellite. Then there's another term which is very, very important when you come to remote sensing, which I want to introduce you to, and we call it resolution. Resolution in remote sensing. Without understanding resolution, you cannot become a remote sensing expert. You cannot be able to do any remote sensing work, because this one is very, very important, because this forms the basis of your understanding of every aspect of remote sensing work you want to do. And there are four types of resolutions, which I'm going to show you. The first type of resolution, we have spatial resolution. And spatial resolution means this is the smallest possible size or feature that can be detected by a satellite. You see, for satellites, when we obtain information or data from satellites, they give us data in terms of images. And images are in form of square, but in GIS language, we don't call them square, we call them pixels, something that is a square in shape, right? Now, every satellite gives these images in different sizes. and that's what we now call a resolution, different sizes. So spatial resolution is the smallest size that any satellite can be able to detect. And what I mean, for instance, I'll give an example. We have many types of satellites. We have Landsat. Landsat, it gives you an image size that is 30 meters over 30 meters. That means we have a square of 30 meters length and 30 meters width. That means that is the pixel, that is the spatial resolution of that satellite. And then we also have another satellite. For instance, we have a QuickBird. A QuickBird has a pixel or spatial resolution of 67 centimeters. That is very, very, very strong. You see, spatial resolution, the higher the spatial resolution, the stronger or the more accurate a satellite is. Because if you can compare like between the two satellites I've given you, the Landsat satellite has a spatial resolution of 30 times 30. And then we have a QuickBird which has 67 centimeters, which means this QuickBird can be able to see very, very minute elements on the ground. Real life example, a Landsat, you can be able, if you're working with Landsat satellite that has a resolution of 30 meters times 30 meters, which means you can be able, if you are looking for vegetation, you can only see trees. You see, you can be able to see the roads, you can be able to see the water. But for the QuickBird, because it has a higher resolution, you can be able to see even the soil, because it can be able to see the very minute elements on the ground. So the higher the spatial resolution, the higher the better the satellite. And then we also have what we call spectral resolution. Spectral resolution describes the ability of a sensor to define wavelength intervals. Yeah, spectral now, I'll give you also an example of Landsat and QuickBird. Let me use the two satellites. A Landsat satellite has 7 bands, and then a QuickBird has 4 bands, which means the lesser the bands, also the more stronger the satellite is. So you can be able, so far you can be able to know that a QuickBird satellite is better than a Landsat satellite. Then the third type of resolution, we have temporal resolution. And temporal resolution, this refers to the length of time a satellite takes to complete one orbit or one cycle. In the normal understanding of orbit, for instance, the Earth takes 24 hours to make one orbit, right? So even these satellites, they also orbit around the Earth. Every satellite has its own temporal resolution. And for instance, I'll also use Landsat. Landsat takes 16 days from point A. It leaves point A day one. It goes round to the same spot. It takes 16 days for Landsat. Then for Spot, another satellite, another type of satellite, it takes 26 days. You see, it leaves point A, it goes round, it takes 26 days to go back to the same spot. Different satellites have different temporal resolution. That means different satellites take different time to make a complete orbit around the Earth. Then the third type of resolution, we have what we call radiometric resolution, and this describes the ability to describe very slight differences in energy. The finer the radiometric resolution of a sensor, the more sensitive it is to detect small differences. This now comes, this is the strength. The strength, you see, what satellites do, we have the sun that gives the radiation, that gives the source of energy to the Earth. And then we have satellite here. So the Earth releases energy from point A, the radiation goes to the Earth, it's reflected, and then it goes to the satellite. So these satellites have different capabilities and different strength to absorb that radiation. You see, and every satellite, for instance, we have Landsat has a strength of 8 bits. We have Spot, which has a strength of 8 bits again. We have Equinox, which has a strength of 11 bits. And also we have others that are able, that have even stronger bits. So the stronger the bits, the stronger the satellite is. So that is the strength to obtain the finer and minute electromagnetic radiation that is there. And for remote sensing, we usually focus on two types of resolution. For every remote sensing expert, we look mostly for two, which is the spatial resolution and the temporal resolution. The the amount of the pixel and also the time it takes to make. So, but this I will explain more below in terms of diagrams so that you can be able to see. So I prepared this. You can be able to see what I was saying here. We have Landsat 8 has a spatial resolution of 30 meters, and it takes 16 days to make a complete orbit. We also have, these are some of the examples of the Landsat. There are so many, there are more than 6,000 Landsat satellites in the sky, but I just decided to give you an example of a few of them so that you can be able to understand. If you can be able to see all these satellites, they have a different spatial resolution and a different temporal resolution. But let me show you how the difference come in. You see, for Landsat 8, it has a spatial resolution of 30 meters. That means its image is 30 meters, 30 meters, and then it takes 16 days. But look at this, which we call spot 7, spot 7. Spot 7 satellite has a spatial resolution of 1.5 meters, which means it's very strong. It can be able to see very minute elements on the ground. And then it takes only 1 day. So you can be able to get that image today, and tomorrow after another 24 hours, you're able to see the same image. Though there are other satellites that take less than 24 hours. For example, we have VIIRS. It's also another type of satellite, but its spatial resolution is very low. It's 375 meters. You see, that means you cannot rely on that if you want to get very minute element. But if you want to get that image, it only takes 12 hours. That means you can get it in the morning, and also you can get the same image of the same area in the evening. But most people today use sport because it takes only 1 day to make a complete orbit, so you can be able to get frequent images. But also remember, in remote sensing, there are many uh, projects that you want to undertake. So every project you undertake also is dependent on the satellite. So if your work, maybe you want to get an image today, you want to get the same image in the next 30 days, you can get any satellite. So every satellite is dependent on the amount of work you want to do. Then from there, I'm going to take you through the next chapter, which is I'm going to have prepared an image of example of image satellites in the sky. There are more than 6,000, as you can see here. So these are some of the satellites I want you to have a look at. So we have that image there. As you can see, there are more than there are more than there are more than there are more than 6,000, but just a few I'm going to show you. So you can see we have a Landsat 7 here, we have Tetra, we have Aqua, we have Aquaris. All these are the satellites in the sky, and they are making, you can see they are in a certain orbit. All these white rays you see here, these are white rays, these are orbits. It's a path. An orbit is a path that a satellite takes to travel around the Earth. So you can see they are all aligned in a certain orbit. You can see like these three. We have the Landsat, they are in this orbit. You can see others are in this orbit. And then you can see also others in this orbit. So all these satellites are following a certain path. Then from there, I'm going to also to show you something else. Uh, so let's look at the next thing. The next thing, we're going to look at the process of remote sensing. Here is where I want you to pay much attention to, because I need you to understand how remote sensing works. You need to know how does it work from the sun to getting the final information, that's data. So there are usually the 7 steps in remote sensing. And all these I've also prepared a diagram so that you can be able to understand. So the first step of remote sensing, we have the energy source, which is the sun, which is point A. As you can see here, we have the sun. As I said, there are two types of remote sensing. We have the passive and active. This is a perfect example of passive remote sensing, where the remote sensing system is dependent on the sun. Because without the sun, we cannot have that energy. So we have the sun, which is point M, uh, which provides the energy, the radiation. Then from there, the radiation travels to the Earth atmosphere. So we go to step two, which is the radiation and the atmosphere. How does that radiation travel from the sun to the Earth? Then we also have step three, which is interaction with the target. So we have the sea, and you know the target, the different types of target here. We have a target of the earth, we have plants, we have water, we have mountains, we have clouds. So there are so many targets that I will explain also below. And then we go to stage four, which is the energy recording by the sensor. Once that electromagnetic radiation reaches the earth or reaches the target, the radiation is reflected back to the atmosphere, and that's where now it meets the sensor. You see, the sensor can only be able to absorb the electromagnetic radiation after it's reflected from the target. So we have the electromagnetic radiation travels from the sun to the target, and then it's reflected now to the sensor. Then stage five, we have what we call transmission, receiving, and processing. Once now the sensor receives that electromagnetic radiation, it now sends the signal to a station. Now at the station, that's where we have the transmission, where the signals received and processed. And then we also have stage six now, the interpretation and analysis, which is done now by the people, the human resource, the people and the computers. And then we have stage seven, which is the application. All these stages, I'm going to discuss them below. So we start with the first stage, which is energy source or illumination. So the energy is from the sun. The sun is the main source of energy, even in the normal life. Without the sun, there is nothing that can be done on this earth. So the function of the sun is to provide the energy that is needed in the remote sensing process. So this energy, once it leaves the sun, it undergoes two steps. Number one, it's reflected. Once it reaches the target, it's reflected. Then step two, it's absorbed. The target is able to absorb the energy, which also going to show you through illustration below. So once the energy leaves the sun, it's reflected, and it is reflected at two stages. Number one, it's reflected by the clouds. The clouds also reflect some energy back to the sky, and also it's able to absorb. And then number two, now the energy that is able to penetrate the clouds and reaches the target, it's also absorbed by the target, and also the target reflects the energy. Then the next step, that is radiation at the atmosphere. The clouds reflect the visible solar radiation and emit infrared radiation into space and provide an indirect measure of the precipitation. This is what I was explaining now. You see here, the sun releases what we call incident energy or solar radiation to the earth. The earth, number one, absorbs that energy. Once absorbs now energy, it also reflects some energy back to space. Now, once it reflects that energy to space, that's where now the sensors are able to absorb now that reflected energy. Sensors cannot absorb direct energy from the sun. The energy must reach the earth so that it's reflected by a certain target. You know, if you're doing a project on plant, or maybe you're doing a project on water, maybe in the ocean, maybe Pacific Ocean, that solar radiation must reach the ocean so that it it can be absorbed by the ocean, and then it's reflected back to the space. Because once it's reflected back to the space, the sensor now is able to pick that signal. You cannot, that's when the signal is now which gives you information about that water. If it's on plants, once the radiation is reflected by the plants and then it's back to the space, the sensors now receive that electromagnetic radiation and gives you information about those plants. Then we have Then we have the third stage, which I was explaining, which is the interaction with the target. So let's look at the interaction with the target. Here is a diagram illustrating what I was saying. So we have incoming radiation from the sun here, and then once we have incoming radiation from the sun, once we have incoming radiation from the sun, it's reflected. These are the clouds. These are the clouds here. Number one, the clouds. The clouds absorb some energy. Then there are also some energy that go through, penetrate through the clouds and reaches the Earth's surface. Once it reaches the Earth's surface, some energy is also absorbed by the Earth's surface, and then some also other energy is reflected back to space. Now at this point is where we find sensors. Sensors are found here, where it now the work of the sensor is to receive and absorb reflected energy from the Earth. To explain that further, I want us to look at how does that happen. I'll give you two examples of how it happens, and one of the examples is vegetation. Why do you think we see plants as green? Why? What do you think? The main reason why we perceive plants as green is because of one thing. You know that we call electromagnetic radiation comes into different color components. And the main color components of electromagnetic radiation, we have the red, the green, the blue. The reason why we see plants as green is not because plants are green. No. The reason plants are green is because once the electromagnetic radiation hits the plant target, the plant is able to absorb all other color components, and then it reflects away the green color. That's why you're able to see plants as green. If the plants, that's why you see some plants are blue, some plants are yellow, some plants are other colors, purple, white, which means the color of a certain target, it that is the color that the target reflects back. It's able to absorb all other electromagnetic spectrum colors, and then it reflects others. So if a color is green, that tells you that plant reflects the green color. If a plant is yellow, that means that plant has reflected the yellow color and absorbed all other colors. Another perfect example is water. Why are oceans blue? Once you see the oceans are blue, right? The oceans are blue because that's the color that the water does not absorb fully. That's the color that the water reflects back to space. The longer visible wavelengths, that is the green and red, are absorbed by the water than the shorter wavelength, which is the blue. That means the blue has the shorter wavelengths in water, and that's why it's not able to be absorbed. And that's why you see the water as blue. So that's why that's how I wanted you to understand in terms of uh, the reaction between the radiation and the target. So once it hits a certain target, the color of the target is a short wavelength color that is not able to be absorbed by that target. So let's go to the next step of the remote sensing process, and that is energy recording by the sensor. The the energy recording by the sensor, as I was explaining earlier, let me show you clearly here. As I was showing you earlier, you can see this is the sun. This is the sun, and these are different targets. We have the buildings, we have the vegetation, we have water. I want to use those so that you can understand. So this energy, once it leaves the sun, for instance, it comes and hits the plants, that electromagnetic radiation, and then the plants absorb the longer wavelength colors. Once it's able to absorb that, the other is reflected, and once it is reflected now, it emits the sensor. So the sensor is only able to get that reflected color. So you can see if it's plants, the sensor is able to receive the color reflected radiation. If it's ocean or water, the color that the sensor is able to obtain is blue. So every target has a specific color that it reflects, and the color it reflects is the shorter wavelength that it's not able to absorb. And then we go to the next step, and that is transmission, receiving, and processing. The stage of transmission, that's where now, after the sensor, after the sensor receives the information, now it sends that data to a certain lab where it emits now people, the human resource, where it emits the computers, and the data is received in several ways. I told you you can receive that data from the sensors by using GPS. If you have a GPS and you go out in an open space, you can receive data of a certain area, of a certain region of your interest. Or you can also use computers. You can also use your phone. You know your phones. These phones are your gadgets. You can turn your phone into a computer gadget, and but that I'll be able to share in the next class, how you can be able to turn your phone into a GPS and obtain all data from satellite. Your phone can be able to tell you how many satellites are visible from your point of view. If I'm standing right now here, I can be able to I can be able to know how many satellites are within this region through my phone. It can be able to show me, and then through that I can be able to translate and process that information to final data. And then the next step of remote sensing process, we have interpretation and analysis. Remote sensing data comes in multiple images, each representing a range of bands and wavelengths. The image, for instance, I'm going to give you an example of two images here. As you can see on the screen, we have one image on the left side of the screen, and also we have the other image on the right side of the screen. The image on the left side of the screen, this image now, here, is what we call the true color composite. What do we mean by true color composite? True color composite, the colors on the image match the real world colors that we see. And then the image on the right side of the screen, it shows the first color composite. Now, when you're downloading these images from the satellite, they come as first color composite. They come as this. You see them like this way. Then it's you now as a remote sensing expert to turn this image from first color composite to red color composite, and you use that. We have for those who know about that, you true color composite. We have the red band, you have the green band, and the blue band, the RGB, the red, green, and blue. So, but that I also show you through the practical that we will have the next session, so that you can be able to understand what I mean by that. So when you download the images from the satellites, they come in terms of first color composite. So they come, you receive them like this, and then you turn them to the real world. See, you see them as the way they are on the ground. And that's why now it takes us back to the definition of remote sensing, where we say remote sensing is obtaining information about an object without being in direct contact with the object. So if I want to get information about a certain mountain, for example, in Kenya where I am right now, I don't need to go to the mountain. I can use remote sensing to get images of that mountain and be able to do work from my place. So the interpretation and analysis is done by computers through your command. You're the person now who commands the computer, and that's what you call uh, classification. We have what you call where you show the computer, you give it the command, or the computer can run itself. But usually, when it comes to this kind of analysis, you are the one that gives the computer commands. You tell it do this, and it does that. So the next step of remote sensing process, what we call the application. And now that this is where we are going to focus, because based on our topic, we were looking at remote sensing trends and future opportunities. What are the opportunities of remote sensing? What can you do with remote sensing? Those are the questions that should be in your mind right now. And another advantage of this area for those students maybe who are maybe taking a degree or taking your master's or a PhD project, you can use some of these applications that I'm going to discuss today and come up with a project for your degree, master's, or PhD project. And one of the applications now of remote sensing is what we call land use land cover classification. Land cover classification is what most organizations, most people always want to do, because using this, for instance, if you are in India, even in Sri Lanka, even Ethiopia, in South Africa, I can be able to show you that country, how is it divided in terms of the resources. For instance, I'll give you this image here. When you look at this image, this is a perfect example of a land use, land cover classification of a certain area in Kenya. So I was able to classify this area using remote sensing, and you can see it's able to give you that area, the urban density. For example, a town, you can see, for instance, the urban density. You can see this maroon color here. That means this place is densely populated. We have so many buildings. Also, it's able to classify the area with agricultural land, grassland, forest, water. So, as a remote sensing expert, you are able to provide so many solutions. Like you can approach even the government, tell them, hey, look at this area, certain area. We have uh, a lot of water catchment. We have a lot of water. We can you can give this information to manage this water. You can see there's forest, you can see there's grassland, you can see there's this much bare land that is nothing, it's just bare. So remote sensing is a 21st century tool to solve problems. Then going physically to the place, it costs a lot. Maybe if, to go on the ground, you take a lot of time going around that area to be able to identify that. But remote sensing does it for you. You just need to obtain images from the satellite, and then you can be able to classify all those data. And then the best thing with remote sensing, it gives you accurate information. If it's terms of forest, it can be able to calculate for you in terms of hectares. What is the quantity of trees, even the number of trees. We have a very high satellites like Econos. You can be able to do tree count of a certain forest, to be able to calculate how many trees do we have. Is it 10,000, 1,000,000? So remote sensing gives you a powerful tool to do land use and land cover classification. This is one of the project areas you can do for your country or your area of interest. Then the next application of remote sensing is what you call urban greenness or eco-friendly work score. You do this using eco-friendly work score calculator. What's the purpose? What do I mean by this? In most in most urban areas, for instance, I give an example of Nairobi. What countries are doing nowadays, every city, there must be somewhere people can relax, what we call green zone. We call them green zones, where the government is trying to make urban centers as comfortable as possible by offering what we call parks or walk parks, nature walks, where people can go and relax. And you can do this using remote sensing. You just need to go use your computer and take a certain city. For instance, this was done. I did this for a certain city in Africa. So using the remote sensing, you can be able to calculate that. And you can see this is using Landsat image here. Landsat image. You can see, because Landsat image has what I was calling a 30 times 30 pixel. You can see you cannot be able to see the minute details. But using the quick bird, which has the 67 centimeters, you can be able to see the finer details. So that's a perfect difference with the satellite. So you can see this on the left side here of the computer. You can see this Landsat image of the same area, and this is a quick bird image. So you can see quick bird image can be able to get you the minute details. So you can be able to see in that city. For example, the green area, that is the forest, the paddy fields, the grasslands, yeah, and then you can see the non-green spaces which are bare land. So, what's what's the purpose of doing this? The purpose of doing green zone analysis is to provide a city. For example, if you can see these green areas, that means you can tell the government, no, don't touch those areas. Those areas can be turned into green zones. So don't construct buildings on them. Rather, you can construct buildings on these non-green spaces, because these non-green spaces means you can construct buildings on them. So this is done using a software or a method called Ndvi. Ndvi is a software or is a system we use in remote sensing, which is a normalized difference vegetation index. And this was done using satellites ALOS AVNI2, which is a ground which has a ground resolution of 10 meters. So you can see real practical issues of remote sensing here. Then another application of remote sensing we call monitoring deforestation. This is one of my projects I did for my degree project back then. I used the remote sensing to show the government how deforestation has happened in Kenya for a period of 10 years, for a period of actually 40 years, since 1960 to 2000. So for the remote sensing, you can be able to monitor forest areas, or what we call deforestation. For instance, you can see this image on the left side of the screen here. This is a 1989 image, a case study of Myanmar. So this I did it to show you the example, and then you can see the same image in 1995. So what can you be able to see here? Here you can be able to see what we call deforestation, and you can be able to see that from here. You can see like this area here of the forest. When you come to 1995, it's not there. So that means the forest has been removed. Okay, and then you can also see some areas here. When you come to 1995, they're not there. That means deforestation took place in Myanmar from 1989 to 1995. That is the perfect evidence of deforestation, and you can do that using remote sensing. You just need to go and get that image from satellite. The next application that I want to show you is what we call surface steepness using LIDAR. For the 21st century, you've realized that it's not like the other years back then. Back then, when you needed to construct a building, when you needed to do some construction, you just went to the site, just looked around, and then you started bringing up buildings. But today you don't do that. You need accurate information, because that's why you see you construct a 10-story building or a 20-story building, and then after 2 or 5 years, the building collapses because you never did a concrete analysis of the area. So what remote sensing can help you, you can do what we call surface steepness analysis using LIDAR. And this you focus on two main things, which you call the DTM and DSM. The DTM is a digital terrain model, and also you do digital surface model. So you're able to know this area, how steep it is. Can you be able to withstand the weight of 20-story building? It also tells you how far in terms of height that your building can go. That ground, how much can it support? So if the model tells you the building can be able to support 10 stories high, and then you construct 20 stories high, then you just causing harm. That is a potential accident in terms of building collapsing, and you can kill a lot of people. So this model using remote sensing can be able to tell you and guide you, this area is suitable for this certain height of building, and then another area is also suitable for a certain height of building. So remote sensing helps you in today's construction industry by giving you the surface steepness of that area. Another application of remote sensing is what you call watershed and an environmental impact assessment. As you can see here, the different images, we have around 5 images. We have this image, we have this image, we have this and this. So this image has been done what we call DEM. DEM is a delineation of that area. So the remote sensing helps you understand. For instance, like this image, it shows you how we're able to spot water in a mountain. You see, mountains and forests act as a water catchment, right? So using remote sensing, you can be able to do analysis of various mountains in your country, if your country has various mountains, you can use remote sensing to do analysis of those mountains to see if there's any watershed. Does it contain any water? If it does contain water, then approach the relevant water authorities and tell them, hey, this mountain has some watershed. Can we be able to tap that water? You know, with the minimum, the least minimum impact on the environment. And also that it can also help you do an environmental impact assessment. How can you be able to harness that water and and channel it to reach the people with causing the least effect or impact to the environment? So remote sensing does that for you. It does a model for you. You do a 3D model on how you can be able to get that water. So remote sensing helps you identify watersheds and also help you in environmental impact assessment. The next application of remote sensing is what we call soil moisture active passive. This is a 21st century way of analyzing soil moisture. Remember, remember, as I was starting of the course, I told you we have different satellites for different purposes. So we have some satellites that are used to determine the soil moisture, and these are we have meteorological satellites, which can be able to know this certain area. That's why you find in the 21st century we have organizations that come and tell you this region can well support bananas, while that the other region can be able to support maize. Why? They're able to do that analysis that we call the soil moisture active passive analysis to determine the soil moisture of a certain area and be able to guide you on how to do your that to help you do know how what you can plant there, because different soils have different moisture levels in terms of the components, and every soil has what it can support best, because soil A can support maize better and soil B can support bananas. If you plant bananas in soil A, they can't grow, and if you plant maize in zone B, they can't grow, because every soil region has a certain water moisture content that, and it can be able to support a certain types of plant, right? And then we also have what you call the surface water and ocean topography. The surface water and ocean topography mission is designed to provide the surface water elevation measurement for the ocean. How do I mean by this? That's why you're able to see remote sensing expert. They can come and tell you this ocean or this river. If you don't use this river in 10 years, the river is going to be dry. Why? Because remote sensing expert, when they use satellites, they can be able to measure the quantity of water in rivers, in oceans, in ponds, in reservoirs, underground. So they're able to show you if you don't use this amount of water in this river effectively, then the next 10 years the river is going to be dry, right? So and that is only done using remote sensing. Another use of remote sensing is what we call uh, use it what we call the grace follow on and the grace 2. There's a new model that has come up with the 21st century. Actually, it was designed back in 2018. The GRACE mission has provided insights into terrestrial water storage for drought monitoring. How does this impact the 21st century world? The GRACE follow on and GRACE 2, it helps you as a remote sensing expert to understand what is the water level. For instance, I'll give an example, a perfect example in Kenya. We did an analysis for a region called Turkana. I was one of the most sensitive expert that was hired by the government to do the grace follow on and the grace 2. And we realized the place is a desert. Turkana is actually the northeastern part of the country that is very dry, that and people are dying because of the lack of water. But when we did a grace follow on and grace 2 analysis, we realized this region has a very huge deposit of water underground that can be able to turn this place to green. It can turn this place from being a desert to a first-class green zone. Yes, using remote sensing, we're able to see it has a lot of water deposit, underground water reservoirs, but can also be able to feed the country, the whole country, for more than 200, 300 years from now if it's well used and managed. So remote sensing is a powerful tool. The last application that I prepared for today is what we call air quality. We have the air quality and the visible infrared image radiometer suit. The the visible infrared imager is what has been used in what we call polar orbiting operation and environmental satellite system. This has been able to collect more than 22 spectrum bands. Remember, when I was explaining about satellites initially, the satellite to the highest number of bands was around 11, 16 bands. But to see this new infrared image reducer suit has 22 spectral bands, which is very, very, very strong. That means it has what we call thermal infrared wavelength. Thermal infrared wavelength, let me explain to you. And I will explain to you in real life situation. Maybe you have watched these movies where we have terrorists, maybe they have held people hostages in a certain building. You know what the police do or the government does? It uses the thermal infrared satellite. That means it sees through the walls. These satellites are very powerful and are being developed to be able to help in the 21st century crimes and also be able to determine to help, for example, in um, in mining. They're very used in mining because they can be able to see through the ground and to see the deposit of minerals and all that. So these are very powerful satellites that are being set up to help in the GIS and remote sensing industry. The last application of remote sensing that I've prepared for today is what we call air quality. Air quality application basically deal with the use of remote sensing to determine the effects of air pollution on vegetation or in urban. Today, we are privileged to use remote sensing. For example, in a city, you can be able to calculate the air quality of a city, of a given city, using remote sensing. How? You can be able, there is what we call the thermal infrared satellite, which can be able to give you the images of CO2, the carbon dioxide images from a city, and all those gases you see in the sky. For instance, you can be able to know, to tell people, to determine the, you see, like we have these reports by World Health Organization, which tells you this is the safest city to live in, this is the safest city to live in, this is the safest place to live in. How do they come without information? They come out without information after doing air quality analysis to be able to see which region is less contaminated in the air by these other gases. So remote sensing, and I'll give an example of Econos satellite. Econos satellite has a very, very high resolution sensors. So they can be able to spot the minute level of air pollution damage. They can be able to spot that. So you can see how much remote sensing is helpful in the 21st century. There are so many other applications, but I wanted to focus on this because these are the real life. And remote sensing, it's applied everywhere. Everywhere. There's nowhere you go you don't find remote sensing because it's a 21st century solution tool. So, and you're privileged to know this because you can use this to turn lives better. Then I want us to look at what are the advantages of the disadvantage of remote sensing. You see, everything has advantage and disadvantage, and I want us to focus mainly on our advantages. The first advantage of remote sensing is it provides data for large areas. Remote sensing can be able to capture data for even a country. You can be able to catch data for Africa, for Europe, for Asia, for the whole world. That is the powerful tool that remote sensing has been able to do. Then the second advantage of remote sensing is it provides data of very remote and inaccessible regions. I'll give an example. If I tell you today, go to Mount Everest and give me and take images of the top of Mount Everest, so you may not even be able to reach there, or you may take the longest time to reach there. But using the remote sensing tools, you just need to your computer go get information from the satellite. So satellite provides very remote and inaccessible areas data. You see, you're able to get data to regions that you can not even be able to access you yourself. Then the advantage number three, it's able to obtain imagery of an area of a continuous period of time. Like for instance, I was saying like forest monitoring, maybe a forest that is far away. For instance, I can be able to get data of a forest in maybe in South Africa and I'm in Kenya. How can I be able to do that? I can be able to do that using remote sensing. So I need just to tap in, take the satellites, provide my area of interest, and then get that data over a continuous period of time. I can be able to obtain that data today. I can also be able to get that data even back then. Like if I want to check the mountain condition of Mount Everest, I just need to go and because the satellite store information, go back in 1960 and be able to observe. I can be able to get the images of that area for a given period of time. Then advantage number five, it's relatively inexpensive compared to employing a team of surveyors. That is what I was telling. Like when you want to do um, analysis of deforestation, maybe in South Africa, I don't. It's much cheaper than sending maybe a team of experts. I tell them, hey, I book you air tickets, go to South Africa, go and give me collect for me data on a certain forest. No, you don't have to do that. You just need your computer, go and obtain all those images. The only thing you can do is what we call groundwork. Maybe you want to go and see for yourself after you obtain all that information. So it's very, very cheap. And then it's also easy and rapid collection of data, very easy. And then also rapid production of maps for interpretation. There are so many advantages of remote sensing. If I was to explain them right now, I'll take hours and hours to explain because remote sensing is a 21st century tool to solve problems. Then what are some of the disadvantages, the shortcomings when it comes to remote sensing? The interpretation of imagery requires a certain skill of level, and that's why we need more people to come in the field of remote sensing. Currently, there are very few, there are almost maybe 5% of remote sensing experts in the whole world, and the amount of work is becoming more and more. It's compiling, right? And that's why we need more and more people to come into place and learn about remote sensing so that we can be able to tackle. Because currently, all fields, all levels of works, you must find remote sensing. Then number two disadvantage, it needs cross verification at the ground. That is the field survey data I was saying. Maybe you are doing an analysis in South Africa. At one point, you will be required maybe to go on the ground to verify that what information you've been getting from the satellite is true, right? Because you'd be very disappointed if you got results from satellite telling you there's deforestation on the ground, and when you go on the ground, you find there's no deforestation. Actually, the trees are becoming more and more. So groundwork is for verification only. And then the disadvantages is data from multiple sources may create confusion. Yeah. This, for instance, maybe you're using a satellite, Landsat satellite, and you're using Econos satellite. They'll give you different information. Why? Because remember we said if Landsat satellite has a spatial resolution of 30 meters, QuickBird has a resolution of 67 centimeters, which means this provides more accurate information than this, right? That's what I was telling you. Every work, depending on the level of work you're doing, you need to be very keen when you're selecting the kind of satellite you're using. Then objects can be misclassified or confused. Yes, if you don't have adequate information about that, how you can classify, you can do it wrongly. Then number five, distortions may occur in an image due to relative motion of the sensor and source. Yeah, for instance, maybe you're collecting information with a GPS. You know, a GPS uses when you want to collect information about with a GPS, you need to stand. You need to be still so that you can be able to connect to the sensors in the sky and collect that information. But when you keep moving the GPS around, that means you're distorting the information because it will be confused. Am I picking information of this area or am I picking information of that area? So you need to be still. So that's advantage of maybe people who are very shaky. You can't hold something very still. You keep shaking and all that, so you distort a lot of information. Yeah. So those are some disadvantages of remote sensing. And then what I can conclude is that remotely sensed data is very important to broad range of disciplines because today remote sensing is everywhere. This will continue to be the case and will likely grow with the greater availability of data promised by an increasing number of operation systems. The availability of this data, coupled with the computer software necessary to analyze it, provides opportunities for environmental scholars, planners, particularly in the areas of land use mapping and change detection that would have been unheard decades ago, right? So you can see remote sensing has continued to be appreciated in the real world by on all aspects of life. When you go to land, you need remote sensing. When you go to water, you need remote sensing. When you come to schools, you need remote sensing. When you come to forestry, when you come to agriculture, when you come to meteorological, but all these areas will continue requiring remote sensing. And even with the future generation, remote sensing will become even a bigger to be an opportunity. So this is my advice to you young people, you young scholars who want to pursue remote sensing. Keep learning because there are a lot of opportunities coming. They're coming, they're there, and they're keeping to grow. So with this information, you never fail to change the world. Let's change this world as remote sensing expert. Join me, join others. Let's use this information. Then I also provided some how you can be able to get this data. I've provided some reading materials as you can see. Remember last time when I was teaching about GIS, I told you need to go and register. Go and register. Go and open an account with the USGS Earth Explorer. Once you register with the USGS, you can be able to have access. Remember, this is free. This is free data. Go click on this link here. I will share this document with the management of SkolarGate, and everybody will be able to get it. So go click on this link. This is USGS. This is a United States Geology Survey, Earth Explorer. Go open account with them. It's free of charge. Won't be charged. It will take only 5 minutes. Visit the account. You'll be able to have access to Landsat images, Sentinel images, MODIS, a lot of satellites free of charge. Also, go and open an account with the Sentinel Hub. You're able to have access to Sentinel, Landsat, Sentinel satellites free of charge. Just open these links, create accounts. Then next week, through the management of ScholarGate, we're going to have practicals on GIS and remote sensing. And we're having a 2-day webinar so that I can be able to train you on how to actualize GIS and remote sensing. So we are going to use two softwares. So I already have provided the link where you can download this software. It's free. No one will charge you. Go download what we call QGIS. Click on the link, download the software, install it in a computer, then wait for next week when I can be able to train you. Also, go and download Google App. It's free of charge. Click on the link, download, and then next week, the data management will be able to do practicals and able to show you what we've been talking to. We've been doing a lot of theories on GIS. What can we do with GIS? Can we do land cover, land use land cover? Yes, I'll show you. You'll be able to see that practically, how you can be able to do that. So thank you so much for that. And I'm very grateful to the management. And what I want to do is that I want to encourage you that you continue learning, you keep learning and learning and learning so that you can be able to achieve more. So I'll share this document that I'll be able to train you today or the management and you'll be able to share. So thank you so much. I will allow a few questions from you. So maybe two ladies and two gentlemen can ask me some questions. So yeah, thank you. Yeah, so I'll ask for some questions. you can ask me some questions, please. Yes, ask me. Yes, I can hear you. Kindly talk to me.